Today I'm here to discuss something on the vortex field. I mean, in the class 2 standard, we always study this kind of setup on Faraday's law, and during in the class we are being taught about the two setups. First is a loop moves in a permanent magnetic field, and the second is a loop at rest in a varying magnetic field. Now, in the first case, it's pretty much obvious that the electric field is being set up by this varying magnetic field. So now in this first case, what is the thing is this, that we know that if there is an electron, let's say if there is an electron, the current will be set up in this direction. So let's say here is an electron. Okay, so now here is an electron. Now this electron this electron will experience a force of QV cross B, and in the opposite direction of the force in which the electron is moving, the current will be in this loop. Now talking about the second case, let's say this is a stationary loop and this is a varying magnetic field. Now the current will be set up in this clockwise direction according to the right hand rule. Now tell me one thing, that if there is an electron in this conducting loop, now as we have seen before that this is the force on an electron or any charged particle, or rather say any moving charged particle. Now tell me one thing, that this electron is not moving, right? This is a conducting loop and this is static conducting loop. This is stationary conducting loop. Now it's not moving, so this velocity is zero. So the force acting on this electron is zero. So how this current appears here? It's a very big question, but what does the teacher say in the class? That okay, there's a varying magnetic field and this current will set up. Let's just remember this thing. But I think that remember something in the physics is a very much useless word. So now just talk about what's really happening here. Okay, so now if there is no V cross B, means QVB, there is no QVB force, and as well as there is no QE force, that is as there is no electric field. So this leaves the only conclusion that the induced current is due to the appearance of an electric field in the wire, and it is this electric field is only responsible for the induced EMF in a fixed loop. So now we are gonna dive deep into this thing. What's really happening? Now, for this we will need some equations. I think you have learned about the Maxwell equations. So now Maxwell assumed that a magnetic field varying with time leads to an appearance of an electric field in space, and it's just regardless of the conducting loop. Now, according to Maxwell, an electric field is being set up by a varying magnetic field. I think you know this equation. Okay, it's a basic equation. Now we all know that this is the equation of flux, and this integration is performed. There's an assumption that this integration must be performed in an arbitrary surface stretched over the loop we are interested in. So in our case, it's the first is this image, or in this case, or in this loop we're interested in. So the integration we're performing will be around the surface or any arbitrary surface stretched over this loop. So now, as we are doing in partial derivative, so I think this is an assumption that we must take. I don't think, I mean, this is obvious. Okay, let's move. So now, if we do this thing, then it comes like b dot ds is equal to on data into ds. Okay, this is all vectors. Okay, this is the equation that it comes. Now notice one thing, that in this equation we have exchanged the order of differentiation with respect to time. So, and integration over the surface. So means this we have changed into this. Now this is only possible since the loop and the surface is fixed. Okay, so we must write that the loop and the surface is fixed. I mean, we are doing this thing for a reason. You will know that later. Means I'm just trying to prove, first I'm trying to prove with the equations, then I will tell what's the really physical interpretation of these equations. Okay, so now if we remember, when we were studying the theorem of circulation of vector b, then we found one equation, like this was the equation. Surface integration b dot dl is equal to mu naught integration of j ds. So now I think you guys remember this thing. So now if we closely look at this two equation, that is the second equation and this equation, I mean, are we getting something? Sorry, extremely sorry. We have to further go on this thing. Sorry, 1 second, man, 1 second. So now if we transform this thing, it means this equation into something like this, we have got this thing now equal to minus dB upon, sorry, it's del t into ds. Now I think everybody can see this 1 and 2 equations are almost, now this 1 and 2 equations are similar. So here the j vector, I mean this, the role of the j here, it is j, and in this case it's like, okay, 1 second. So in this case it's dB by dt, and in this case it's j. So now we can draw our final conclusion that if we from the differential form, then it will be like cross E equal to minus dB by dt. Sorry guys. Now curl of electric field is equal to minus dB by dt. So I think this is the most important equation that we have derived. Now I will explain what's the physical interpretation of this and how I am telling that, or Maxwell told that an electric field would be generated from a varying magnetic field. So now this equation thing, now this equation just explain is a very important equation. So now if you look closely, this is a relationship between an electric field and a magnetic field. Okay, so the time variation of magnetic field B at a given point determines the curl of vector E at same point, sorry. So see, now we had learned in the electrostatics what you have learned, electrostatics what you have learned, that electric field is a potential field, right? It's a potential field. So now, if electric field is a potential field, then curl of field must be zero, okay? But here what you are saying, it's not equal to zero. So this tells that there must be an electric field, which is not a potential field. Now, why I'm telling about this equation, about this two equation, because from this equation we determine that B field is a vortex field, okay? Is a vortex field. Now we can draw this conclusion as we have derived this equation, so we can draw this conclusion that electric field can be either a potential field, what we have done in electrostatics, or a vortex field. Okay, so now vortex field, if some of the guys don't know what vortex field is, then in simple words, the vortex means the rotating part of a tornado or any fluid, okay, like in a fluid. So why we are calling this magnetic field a vortex field? Because if we see that if this is a magnetic field and an electron enters here, then it just rotates in a circle, and I guess that's why we call magnetic field a vortex field. Now we are just saying the same effect here. What is the effect? Like what we are saying actually. We are saying that this magnetic field, this varying magnetic field, generates an electric field which is determined by this equation, minus dB by dt. And this electric field, what it does, it just moves an electron in this direction. That's why a current is generated in this direction. So now the teachers who tell that, just remember this, it's not the fact. The fact is, in this case, the electric field is not behaving as a potential field, it's behaving as a vortex field. So it's a very interesting concept. And if you want to explore more into this, I think you have heard of Betatron, and this vortex electric field has found a brilliant application in the induction electron accelerator, which is also known as Betatron. So now it's not our subject, but the thing is what we have learned in +2 level. This is the explanation of this. So yeah, this is it. This is the concept of vortex field. Thank you. Hope you like this.